All right, let's get right into it. If you've spent any time in networking, you've heard of OSPF. And you've probably also seen terms like designated router and thought to yourself, I keep seeing this, but nobody ever actually explains what it is. Well, you are not alone. Today, we are going to pull the curtain back on one of OSPF's most clever solutions to what is, frankly, a really chaotic problem. But before we can appreciate the solution, we've really got to understand the problem. So let's start with a basic question. What do you think happens when every single router on a shared network tries to talk to every other router, all at the exact same time? Spoiler alert, it is pure chaos. So to set the scene, let's picture a network that we all know, something like a typical office setup. You've got a bunch of routers all plugged into the same switch. Everything seems to work fine, but underneath the surface, there's a specific kind of environment that makes OSPF do some very interesting things. And that environment has a name. It's called a multi-access network. Ethernet is the classic example. Because it's a broadcast technology, when one device sends something out, literally everyone else on that segment hears it. It's kind of like putting all your routers in the same big room. They can all see each other, and they can all start a conversation with anyone else. Now, you'd think having a ton of neighbors is a good thing, right? More connections means more information sharing. But in networking, just like in real life, being too popular can lead to a whole lot of noise and some serious performance problems. Okay, so just how bad are we talking here? Let's imagine a pretty modest network, nothing too crazy. Let's say we have 50 routers, all connected to that same switch. How many one-on-one neighbor relationships do you think they'll try to establish? The answer is over 1,200. Yeah, 1,225. And that number isn't just pulled out of thin air. It comes from the formula for creating a full mesh of connections. In this scenario, every router tries to become best friends with every other router. It creates this incredibly complex and tangled web of conversations that just grinds everything to a halt. This chaos really breaks down into two massive problems. First, you have what's called exponential adjacencies. All those relationships eat up your router's memory and CPU just trying to keep up. And second, you get these insane LSA floods. So if one router has an update, it screams it to all 49 of its neighbors. Then each of those 49 routers turns around and screams the exact same news to their 48 other neighbors. It's a massive, wasteful echo chamber of redundant information. So how did the geniuses behind OSPF solve this mess? Well, they did something really elegant. They didn't try to shut everybody up. Instead, they organized the conversation. They had the routers do something very democratic. They hold an election to choose a spokesperson. And this spokesperson has an official title, the designated router, or DR for short. Its job is incredibly important, but also really simple. Instead of everyone yelling at everyone else, all the other routers on the network now send their updates to just one place, the DR. It becomes the single source of truth for that entire network segment. Of course, you might be thinking, wait a minute, that sounds like a single point of failure. And you'd be absolutely right. So what happens if the DR goes down? Well, OSPF is way ahead of you. The routers also elect a backup designated router, the BDR. You can think of it as the vice president. It listens to everything, builds the exact same network map as the DR, and is ready to step in and take over instantly if the DR disappears. So, after the election, you end up with a very clear structure. There's the DR, the spokesperson, the BDR, the backup, and then there's everybody else who get the not-so-glamorous title of deauthor. This changes everything. A deauthor doesn't need to talk to other deauthors anymore. They only form full, meaningful relationships with the DR and the BDR. I mean, just look at the difference here. We go from the absolute chaos of a full mesh, that spider web of connections, to the beautiful simplicity and order of a hub-and-spoke model. That tangled mess of over 1,200 relationships is just gone. Now, each regular router only has to worry about maintaining two important connections. It is a huge optimization. Okay, so we get why the network desperately needs a DR and a BDR. So the next big question is, how does this selection actually work? What are the rules? Turns out it's surprisingly straightforward. It's really just a two-step process. First, all the routers on the segment compare their OSPF interface priority. It's just a number you can set, from 0 to 255. The router with the highest priority wins. Simple. But what happens if there's a tie? Which, by the way, happens all the time since the default priority for everyone is 1, well, then we move to the tiebreaker. The router with the highest router ID wins. So what is a router ID? You can just think of it as a unique name tag for each router in the OSPF world. And it's not chosen randomly. There's a strict pecking order. A router will always prefer an ID that you've manually configured. If it doesn't have one, it'll use the highest IP address on one of its loopback interfaces. And if it doesn't have one of those either, it'll fall back to using the highest IP address on any of its active physical interfaces. Let's look at this table. It makes it all click. Okay, R4 has a priority of 100. Nobody else is even close. Bam, R4 becomes the DR. Now, who has the next highest priority? That's R2, with 50. So R2 becomes the BDR. That means R1 and R3 are just D others. And notice, even though R3 has a higher router ID than R2, it doesn't matter one bit. Priority is king and it's checked first. Now here's a rule that you absolutely have to burn into your memory because it's crucial for network stability. There is no preemption in the selection. What that means is, once a router becomes the DR, it holds that title for life, or at least until it fails. A brand new router could come online with the highest possible priority of 255, and it cannot force a new election and steal the job. This is by design, to keep the network stable and prevent constant changes. All right, so we've organized the conversation. We have a stable system with a spokesperson and a backup. But why? What's the end goal of all this? Well, it all comes back to OSPF's #1 mission: to build a perfect map of the network so that every single router can figure out the absolute best and fastest path to get anywhere else. See, OSPF doesn't think in human terms like fast or slow. It thinks in terms of cost. Every link in the network gets assigned a cost based on this formula you see here, and OSPF will always choose the path with the lowest total cost. So for us, lower cost just means a better, faster link. But here is a massive gotcha that trips up so many people in modern networks. The default reference bandwidth in that formula was set decades ago, when 100 megabits per second was considered lightning fast. Look at what happens today because of that old default. A 100 meg link, a 1 gig link, a 10 gig link, even a 40 gig link, they all end up with a cost of 1. As far as OSPF is concerned, they're all identical. It's completely blind to these massive differences in speed. And this is a huge problem. It means OSPF might choose to send traffic over a congested 1 gig link when there's a wide open 40 gig link sitting right there totally unused. The solution, thankfully, is really simple, but it is absolutely critical. You have to go in and adjust that reference bandwidth on all of your routers so that OSPF can see the true speed of your links and make smart decisions. And that really gets to the heart of it. OSPF is brilliant. It's incredibly powerful, but it's not magic. It can only work with the information that you give it. From bringing order to chaos with a DR election, all the way to calculating the fastest paths based on cost, its success depends entirely on getting accurate data. And that leaves us with one final thought. Your network is only as smart as you configure it to be. So are you telling it the whole truth?